Welcome to Linear Algebra, Section 1.4, Sums and Direct Sums. In this section, we extend the notions of the sum of two vector spaces and the product, or what we normally call the cross product, or direct product of two vector spaces. So, as normal, we start out with a vector space V over a scalar field K and two subspaces U and W. And we've already defined the sum of two vector spaces in the normal, usual way. The sum of U plus W is the set of all vectors, little u plus little w, where U is in U and W is in W. All right, we saw that in section 1.1. And we also have seen now that the sum is a subspace of V. That was a turn-in homework. Now, when we have the two subspaces U and W of V, well, we're going to say that V is the direct sum of U and W if there exist unique vectors, U and U and W and W, so that for every V and V, V is equal to U plus W. And this goes right along with the concept of a basis for a vector space where every V and V can be written as a unique linear combination of scalars, x1 through xn with v1 through vn. So those two ideas go parallel in this discussion. Now, Theorem 4.1 gives us a criterion for determining, not just using the definition, but when is a vector space the direct sum of two subspaces. All right. Theorem 4.1. V is our vector space over K. U and W are our subspaces. First, if V is the sum of U and W, and if the intersection of U and W is trivial, only the zero vector, then V is the direct sum of U and W. The proof is simple. Let's look at it. All right, so start with an arbitrary vector V and V. So we know now, of course, that V is the sum of U and W. So we know there exist vectors U and U and W and W with V equal to U plus W. But to show the sum is direct, we have to show that these two vectors, U and W, are unique. That is, that they're the only ones. Well, suppose they're not unique. Suppose there exist other vectors, U prime in U and W prime in W, with V equal to U prime plus UW. So now we have two representations for V, and we have U plus W equal to U prime plus W prime. So that means, of course, that U minus U prime is equal to W prime minus W. But now if we rearrange that equation to write it as U minus U prime, let's remember that that's closed under vector addition, right? So U minus U prime is in U, and W prime minus W is in W. But remember our hypothesis that the intersection of U and W is trivial. So that means that u minus u prime is the zero vector, and w prime minus w is the zero vector. Hence, u equals u prime and w equals w prime. So that proves our theorem that the vectors u and u, w and w, when the sum is direct, is now unique, knowing that the intersection of u and w is 0, only trivial. So that's the criterion for the sum being direct. The only vector that u and w have in common is the zero vector. All right. So as a matter of notation, we say the sum is direct and we write the plus symbol with the circle around it. All right, theorem 4.2 tells us the following. Again, let V be a finite dimensional vector space over field K. Let W be a subspace of V. Then there exists a subspace U of V so that V is the direct sum of W and U. But now notice, very important, that the subspace U is not unique. Generally speaking, there exist many subspaces U, so that V is the direct sum of W and U. And it depends upon the basis that we choose for both V and W. Later on in the course, when we discuss orthogonality and perpendicular subspaces, we will have a procedure for determining a particular subspace U in the context of what we call orthogonal complements. All right, so noticing the proof of theorem 4.2, very simple. So we first choose a basis for W, then we use corollary 3.6 from the previous section to extend the basis for W to be a basis for the whole space V. Remember that? So if we have V1 through V sub R as a basis for W, and then we add in vectors VR plus 1 to Vn to be a basis for V, then the extension vectors VR plus 1 to Vn form a basis for U. So that we have then V is the direct sum of W and U. Okay? And then naturally following that theorem, we have a very important result in theorem 4.3. Theorem 4.3 about dimensions and direct sums. Theorem 4.3 tells us that when we have V written as the direct sum of U and W, then the dimension of V is equal to the dimension of U plus the dimension of W. All right. Now, again, the proof is straightforward. Start by labeling a basis for U and also for W. All right. So let's let U1 through U sub R be a basis for U, and let W1 through WS be a basis for W. In other words, we're saying the dimension of U is R and the dimension of W is S. And we're trying to show the dimension of V is R plus S. Okay? Now, every element of U can be written as a unique linear combination of scalars xi with the basis vectors ui, and every vector in W can be written as a unique linear combination of scalars yj with the basis vectors wj. Hence, that means that every vector v and v can also be written as a unique linear combination of all of those vectors, the xiui's plus the yjwj's. So that proves that putting all of them together, the ui's and the wj's, form a basis for V. And that also proves our theorem that the dimension of V is the sum of the dimension of U and the dimension of W. Okay? Now next, let's take U and W out of the context of being subspaces of a given vector space, and let's suppose now that U and W are arbitrary vector spaces over a field K, not necessarily subspaces of a given vector space V. Now, we're going to define what we call the direct product, or it's also called the cross product. I believe that's the name in Cal 3. The direct or cross product of two vector spaces, and it's really the same definition as looking, for example, at, in R2, ordered pairs in R2, for example, or K2. The direct product of U and W is simply the set of ordered pairs U comma W, where U is an element in U and W is an element in W. Very simple. And just like in R2 or in K2, when we have two ordered pairs, we add them component-wise, coordinate-wise. And we multiply an ordered pair by scalars by multiplying each component by that scalar. So with those normal definitions of vector addition and scalar multiplication, we immediately see that the direct product is a vector space. Now, the most common example is if n is a positive integer and if r and s are positive integers with n equal to r plus s, then we can write the vector space Kn as the direct product of the two vector spaces Kr with Ks. Okay? Now next, we have a very important result. The book says it's easy to prove, but I differ with that opinion. And it's here it is. The dimension of the direct product of U and W is equal to the dimension of U plus the dimension of W. Now it says the proof is easy and left to the reader. Well, I don't think it's very easy. I have it written out on the right-hand side of your screen. So I want to look at the proof of this result. And it's the same as saying that the previous theorem we had, theorem 4.3, where we had a direct sum, and v, the dimension of v was the dimension of u plus the dimension of w. Okay. Proof. Start out by labeling bases for both u and w. So let u1, u2 through u sub r be a basis for u, and let w1, w2 through w sub s be a basis for w. So again, the dimension of u is r, and the dimension of w is s. We claim that the following set B is a basis for the direct product. What we're going to do is take the basis vectors for u, u1 through ur, and we're going to tack on as a second coordinate the zero vector of w. And similarly, take the basis vectors from w and add on to that the zero vector from u. So that now we have a set of ordered pairs with the u's from 1 to r and the w's going from 1 to s. So we have a set of r plus s ordered pairs in the direct product. And we're claiming that this set B is a basis for the cross product of u and w. Indeed. Let u be a vector in u and w be a vector in w. So by definition of the basis, we have u can be written as a unique linear combination of xi ui's, and I suppress the notation with the summation notation. U can be written as the sum, I goes from 1 to r, xi ui, and w can be written as the sum, j goes from 1 to s, yj, wj, okay? All right, where we have, of course, that the ordered pair uw is an ordered pair in the cross product. And we can write the ordered pair uw as the sum of the following two vectors. All right, the summation I1 to r of the scalar xi with the ordered pair ui, zero vector, in w, plus the summation j1 to s of the yj scalar with the zero vector in u with the second component wj. And so we can immediately see then that B spans or generates the direct product. And then next, we also have to show that these vectors are linearly independent, don't we, for it to be a basis, right? They have to be linearly independent. So take the sums, the linear combinations, set it equal to the zero vector. The zero vector in the direct product is the ordered pair 0, 0, where the first component is the zero vector in u, and the second component is the zero vector in w. Okay? Now, so what we do is we set the UI vectors equal to the zero vector of u and the wj vectors equal to the zero vector in w. But since those are bases, the ui's form a basis for u, and the wj's form a basis for w, then we know they're linearly independent. Hence, that means all of the xi scalars are 0, and all the yj scalars are 0. Hence, these vectors are linearly independent, and they form a basis for the direct or cross product. So I would not say that it's trivial to prove. And so now we have it. The dimension of the direct product of u and v is the sum of the dimension of u plus the dimension of w. Finally, in this section, we're going to look at extending the idea of direct sums and direct products to any number of subspaces. So now let v1, v2, dot, dot, dot through v sub n be subspaces of v. We shall say that v is the direct sum of this finite set of subspaces, okay? And here's the notation for it. V is direct sum. I goes from 1 to n of vi. v1 direct sum, dot, 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 direct sum v sub n. If for every v and v, there exist unique vectors, v1 in v through v sub n in v, with v equal to the sum, v1 plus v2 plus dot, 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 plus v sub n, where v sub I is in v. Now, you can also prove an extension theorem from theorem 4.2, I believe it was, at the beginning of this section, where these subspaces, VI, have to be their intersection is trivial. So the intersection, say, of VI with VJ is the zero vector. So the intersection of any two of them is only the zero vector. And then next, we define, suppose that W1 through W sub n are vector spaces, all right? And we define the direct product of the vector spaces. And we use a capital pi symbol. Pi going from I goes from 1 to n. Wi is, by definition, the direct product, W1 with W2, dot, 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 to Wn, and it's just the set of ordered n tuples, W1, W2, dot, 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 through W sub n, where Wi is an element of capital Wi. With addition and scalar multiplication defined in the usual way, component-wise, by adding corresponding components and scalar multiplication, multiplying every component by that scalar. So with the normal definition of vector addition and scalar multiplication, the direct product of finitely many vector spaces is, again, a vector space. No surprise there. All right, so in conclusion, here on page 22, I just worked out number 4, and I would like for you to do number 1, but we're going to turn in exercises 2 and 3 on page 22. And that concludes our video for section 1.4.